The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
Okay, good afternoon, everyone. What I want to start on today is talk about really what aggregate is optimal. And the short answer, not to take away from the rest of the talk, but the short answer is it depends. Like a lot of things in life, depends on the application and your materials and other constraints that you have. So what I want to talk about today is some of those constraints and try to put packing into context of where it's useful to look at, where you need to look at a broader set factors. And hopefully that will set up for the other speakers after me that have done a lot more work on packing models and have a lot of their own experimental data to show, to add to this. So first of all, we think about packing of aggregate and concrete to put things into context. We can think of concrete as a suspension of aggregates and paste. So the tighter that we can pack in the aggregate, the less paste and air we need, and the less and the more aggregate we can have. And that obviously has advantages for economy, for strength and durability, and for workability. But we can also think about packing in the sense that we have packing of just the bulk aggregate itself, which is sort of what you see on the right here, which is useful to know, of course, but then it's not exactly how aggregates are in concrete. So those aggregates have to flow past each other. They have to interact with each other. So the shape and the angularity and texture of those aggregates provides one more dimension that we have to consider beyond just how tightly do those aggregates pack. That affects the additional paste that we have to add to separate the aggregates beyond what they would otherwise need if they're tightly packed, and also the rheology of that paste that's needed to suspend and support those aggregates. So at the end of the presentation, after I've talked about everything else with this, I do want to go back and talk about putting this all together and using it for proportioning a concrete mixture. So when we talk today, there's a couple of different ways we can define the solid particles in a concrete mixture. So the way that I'll generally talk about it in my talk today is basically from the 75 micron size and higher. So all of those materials, we're looking at the combined grading and packing and other characteristics of those materials. So we're looking at the aggregates. We could actually include the cementitious materials and the powdered materials, which we could define as finer than 75 micron. And that's an additional step, and we could do that. I'll talk a little bit more later about why we don't. So what I'll do today is the 75 micron size. We can make a split between coarse and fine aggregate, but really we want to put all those together and look at how all of those materials interact. We could also go down and we could make another distinction between colloidal and non-colloidal particles. So once you start having interaction between the particles at a colloidal level, they behave much differently than at a solid level. So we would want to say that if we did look down and include the powder as part of the aggregate, let's say, and look at that whole combined distribution, we probably want to stop at the colloidal particles. But from a practical standpoint, we'll say that the 75 micron as powder being below that and aggregate being above that, and we'll focus on the aggregate above that. So why consider packing density? Because, like I said before, it provides indication of the voids content, which we need to fill with paste and air. And the more aggregate we have, we know that, depending on the characteristics of the aggregate, improves our strength, stiffness, creep, drying shrinkage, and permeability. Packing and workability are closely linked, but they're not the same. So the factors that affect packing also affect workability, but it's not the same function for both of those. So when We talk about the aggregate for optimal packing is not necessarily the same as for workability. And so if you look at what packing is optimal, really we can say that aggregate should be as dense as possible, but not more so. And the reason is because we have constraints that are related to the application. So some of those constraints may be the maximum size for the aggregates to pass through reinforcement. There's requirements for workability, finishability, pumpability that I'll talk about. I'll talk about segregation and how packing and particle size distribution are related to segregation. So that we have to keep in mind. Strength and stiffness are cementitious materials requirement. And then there's just the practicality of making concrete and ready mix, and that we are limited to local available materials. And in the plant, we may even be limited by the bin space and the number of different aggregates that we can blend. So we have to work within all those constraints to basically get the aggregate as dense as we can, but not more. So to go into a little more detail about those constraints, we have the maximum size. So it's well known that as we increase the polydispersity, or the range of sizes, and the diversity of sizes that we have, we will result in higher packing density and lower viscosity. So that's a good thing. We want to have a broader range of particle size, but we're limited based on passing ability, based on ACI requirements for maximum aggregate size. And we also know that as we increase the maximum size, our potential for segregation increases. So we have to keep that constraint in mind. For workability, typically most of the research that's been done has come back and said that that you need a grading a little bit finer than what's associated with the maximum packing density. And I'll show a graph in a moment that from a workability perspective, that's preferred. And then also with packing, if you have, let's say, a rounded natural aggregate with the same packing density as an aggregate that's crushed and has angular shape, the one that's ball-shaped is going to have better workability, even if they have equal packing density. And so there's a shape factor above and beyond the packing density that has to be considered. And then things like pumpability. If we're pumping that aggregate, the layer of material at the wall of the pump, if we're finishing a material, that mortar layer that comes up to the top is going to be much different than the bulk concrete. And so it's the characteristics of that layer that are important rather than the overall bulk packing. So our bulk packing may not be optimal, but our pumpability or our finishability or any of those other abilities are going to be better. And then for strength and stiffness, coarse aggregate, if you look at the crushed aggregate, we're going to have higher strength generally than a rounded aggregate. Even then the rounder aggregate may give us better packing and workability. And then the modulus elasticity is highly dependent on aggregate stiffness. So we may have to give up some packing in order to get higher stiffness from a dense crushed aggregate. The next constraint is segregation resistance. And this table here was based on data that was in François Deloard's book on concrete mixture proportioning. So he looked at different particle size distributions, and he calculated two things. He calculated the packing density and the segregation potential. So with segregation potential, the higher the number, the higher the potential. And so if you look at the maximum density he was able to produce, it was 0.929, and you can see the distribution that was associated with that. The gap grading was almost identical to the maximum density. You have very good packing from a gap graded mix. And in fact, if you test in concrete, there's other results by other researchers that show that a gap graded mix will give you low viscosity, high packing density, but it also gives the highest segregation potential. So it does work well for rheology, but it's not the best for overall concrete performance when we consider segregation. His distribution with minimum segregation actually had a pretty high packing as well compared to the others, and a much lower potential for segregation. And that distribution they'd recommended was essentially the same volume of material in each size. if you look at a uniform distribution on a log scale where we have more at fine materials, that gave fairly high segregation potential, as did the fuller curve, or the 45 power curve shape, which has more coarser particles, and that one also gave high segregation. So segregation and packing are things that have to be taken into consideration. The next constraint we can talk about is our cementitious materials. So in general, we have cementitious materials. Those are going to affect the packing of the coarse and fine. So when we look at coarse and fine aggregate in isolation from the cementitious materials, the optimal packing we calculate for the aggregate may not be the same once we consider the cementitious materials. And so in general, in the literature, and the rule of thumb is that if the size of the particles differs by 10 times, there's no interaction between those particles. You can think of it as a suspension of coarse aggregate and fine aggregate and paste, kind of like I showed before. In reality, we don't have that. We don't have that big of a gap between our powder size and our aggregate. So we're really making a simplification there. One that still is fine, but we do need to realize that cementitious materials are going to affect the packing. And so very often our cementitious and our cementitious materials is driven by strength and durability. So we need a certain amount of cementitious materials that it may be greater than if we took the packing density of the powder, the fine aggregate, and the coarse aggregate, and determine the optimal amounts of all of those to get maximum packing. So we can have a mix that has 400 pounds of cementitious, or one that has 1,000 pounds of cementitious. That's being driven by the strength and durability requirements rather than the packing requirements, and we have to do it. And so, generally speaking, as we go to higher cementitious materials content, we can reduce the amount of fine aggregate and still have a good rheology to that concrete mixture. Another caveat to make about packing is that the packing near the optimal often doesn't vary very much. So this is a chart again from Idealized, and you can see this is the packing density that's plotted against the fine fraction. So this is putting a coarse fraction and a fine fraction together. And you can see with this that as we're at a very low volume of fine fraction, anything we add, any coarse aggregate we add to this, increases the packing density dramatically. Likewise, if we have all fine and we add coarse, we increase the packing significantly. But then when we get here to the maximum packing, we can observe two things. So first of all, we can change the fraction of fine and coarse and not have a big effect on the packing density. It's pretty flat in this range. If we get precise and we pull out the optimal packing, we're at about 30% fine fraction, and most concrete mixes are going to be somewhere between 50 and 40% of the fine fraction. So this, like a lot of times, it's a little coarser than what we would say is a good blend of aggregate for our workability requirements. So the two real takeaways from a graph like this, and this is one example. There's many others from Rheology's book and from other research in the literature that would tell us that two things. One, packing doesn't vary much as we change our grading near the optimal, and the optimal tends to be a little coarser than what we would normally choose for a concrete mix. And so if someone shows data and they say, well, grading didn't affect the workability very much, it could have been that they were just near the optimal and they were showing you a very small range where packing didn't really, or grading didn't really make a big difference on the packing or the rheology. But that doesn't mean that packing is not affected by grading. It just means that you were looking at the narrow range and not the full context. And this can actually be quite powerful when we look at powders and packing of the powder range, because normally if we're using C33 aggregates and we're using conventional blends, we're already in this optimal zone. But in powders, there's sort of more opportunity to improve packing. So there's different idealized particle size distributions that will try to reach maximum packing, maximum workability. The Power 45 curve is probably the best known. So this is the diameter of a given particle size over the maximum diameter raised to a power. The original curve by Fuller and Thompson had that to the 0.5. A variety of numbers have been suggested for that exponent. The Power 45 curve is best known, but other researchers have suggested as low as 0.2. And then there's other variations on this curve that have been developed. But even going back to 1968, here's a quote from T.C. Powers in his book. He says that there is no such thing as an idealized grading for concrete. And basically he suggests that we abandon the search for this. But in reality, we need to have a starting point and recognize that picking a grading depends on packing and a number of things and a number of constraints. And as engineers, we need to optimize within those constraints. So like I said, the Power 45 curve has done well for a lot of people. And you have the size here raised to the 0.45. You have a line that goes from the maximum size to the minimum size. So if you're looking at just coarse aggregate, you would obviously do it to the number 4 sieve. If you're looking at just the coarse and fine, you would draw to the 75 micron sieve. If you're looking at powder, you would maybe take it down to 0. And a couple things with this curve is that, first of all, you can use a lower number for instead of 0.45, you can use 0.35, as low as 0.2. Those will give you a finer grading and potentially higher packing. So there's a limitation. You can't go too low, but generally you'll get higher packing and a finer curve from those. So again, that's kind of taking us away from those coarse distributions that we had before. Again, we want the curve to be a straight line. So mathematically, if you calculate this out, the line should be straight. If you cut at a certain size, so if you say 75 micron and above, and then 75 micron and below, you would have basically a straight line from 100 to 0, and then another straight line for the smaller size below. And so this is really an effective starting point for aggregates. It's not the only thing you should look at, but it is one of several things you should look at. You should also look at the overall distribution of aggregate and how that affects the segregation. There's models for packing-nicity. You'll probably hear more about those in the other presentations today. So again, there's really two purposes. The first is to determine what the predicted packing-nicity is. So I need to know that I have 68% packing, and the rest is going to need to be filled with paste. So I need that number in my mix design. The second is to determine the optimal blend. So say I need 60% of coarse aggregate and 40% of fine. When I use these, I need to consider two things, like which one am I using it for? Am I using it for one or both? How accurate is with respect to those purposes, and what data is needed to get accurate results? Do the models consider the particle shape? How do they take into account the particle size distribution, and what's needed as an input for that? So I'm not going to go into those today. There's quite a few models. But if you look at those models, those are really the two things to look at in deciding whether that is useful. So that's to get your packing, but what we really want to know from a concrete standpoint is the viscosity. And there's a number of equations for concrete. The challenge with concrete is that it's a highly concentrated suspension. And so the models that are out there that you'll see generally are for much lower concentrations. And the Krieger-Daugherty one is a good one to use for illustration purposes. So basically it's the viscosity of the concrete as a function of the viscosity of the suspending medium, which would be paste. And then you have the packing of the solid particles to the maximum packing. So as we increase the maximum packing that we can have in a material, obviously we're going to decrease the overall viscosity and allow us to put a higher volume in of the material. And then there's another term here that's called the intrinsic viscosity, which is this eta in brackets. And with that, that's primarily a function of the shape. So again, it shows us, like I showed before, that we have this additional shape factor that we have to consider when it comes to looking at packing and rheology. So it's the packing, but it's also the rheology. So to put all this together, if you look at the aggregate suspension proportioning method, which was originally something I was involved in. It's just now been balloted and has passed ACI 211. It will be published as a tech note 211.6t, and it puts all this together in a concrete proportioning method. So we select the combined aggregate, and there's criteria for that. Then we have to fill that with the voids in that compacted aggregate with paste and air, and then we adjust the composition to get the right hardening properties. So there's 9 steps to the method, and this will be out soon. From ACI, so you can get on the ACI website and go through this. For aggregate, again, we use the Power 45 curve, and we look at the percent retain chart to make sure that we have the similar amount on the different sieve sizes to get the optimal packing. We balance, or the optimal, not the optimal packing, the optimal aggregate, and we put that together, and then we look at the effective shape. And shape comes in, again, explicitly in looking at the amount of paste. So we need paste driven from the packing density in the voids, which we measure empirically. But then also we add an additional shape factor, so the better shaped, the less paste above and beyond what you need just to fill the voids. So you have paste to fill the voids plus extra paste to separate the aggregates, and that extra paste is driven not by the packing directly, but by the shape of the aggregates. And so that's what you see here. The better the shape, the less additional paste that you need. And then once you have the aggregates, you fill it with paste, then you determine the composition of that paste in order to get the optimal concrete. So to summarize, when we look at aggregate packing, it's one of several factors to take into consideration in selecting aggregates. It's important, but it's not the only factor to consider. Gradings that are finer than the maximum are generally preferred. The max packing are generally preferred. And we have to consider both packing and the shape. So just packing of a poorly shaped aggregate is not going to give us the best workability and the best concrete. And when we do look at it, we want to look at the combined solid particle distribution. And then the way to put it all together is to look at the aggregate suspension mixture proportioning method, which will soon be in the next few months, ACI 211.6t, to look at packing density and then how all that fits in with the overall concrete mix design. So with that, I thank you for your time this afternoon.